Hello everyone. In this third lecture of Graph Neural Network series, I want to talk about how you can train, test, split your data, define your model, train and test functions, and then model training and evaluation. So in the last video, we saw how we can generate graphs from the smile strings of the molecules, and basically there are two ways. One, you can generate a list of graphs, and another way you can store these graphical data in your CPU memory using in-memory dataset. And yeah, so in this video we will move ahead and we will see how we can first train, test, split our dataset. So we wanna split our data set into training and test set in the ratio of 18 to 20. So basically 80% for the training and 20% for the testing. Now the length of our data set is, if you remember, it's 4192, which we can get from this line of code. And we want 80% of it as a training size. So train ratio, which is 0.80 multiplied by dataset size, would give us the train size, and rest would be test size. So test size would be dataset size minus training size. Next what we want is we wanna split using random split method of Pytorch. So up here I have imported a random split from torch.utils.data, and that's what we are gonna be using for splitting our data set. So down here what we need to put in is our graph list. Again, you can put in the lipo variable as well if you have saved your data in your in-memory data set, like what I have defined above here. But I'm just using the graph list. It would not really change anything. Second, we need to put in the training size and test size as a list, and then the generator. So generator here is for reproducibility. Basically we are putting a manual seed of 42. So every time you change this manual seed, you will get a different train test split, since this is a random splitting. So you can play around with different train test splitting seeds. Here I'm just using 42, which is the standard one. So let's run this. And okay, we have split our data set into training and test set. Now let's say we wanna see our training and test set. So what we can use is we can use this indices attribute on train data set, which would furnish the index values, and then we will slice our final data set or our raw data set based on these indices. So if you run this would be our training data set with a size of 3353. Similarly, you can use the same thing for test, and this would be our test data set with 20% values, which is equivalent to 839 data points. And if you want, you can also go ahead and save this if you want. So test and in here you can just test.to as CSV and test set. So you can do that as well. Yeah, so next, just to check the length of our training set is 3353, and length of our test would be 839. Right. So next we wanna use data loader. So data loader is a utility that provides an efficient way to iterate over data sets. It would make it easier to train and evaluate machine learning models, and this is used for batching mainly. So we can put a batch size of 32, 64 or whatever we want. You can shuffle your data set using this. You can run multiple workers or processors to load the data in parallel. You can use collation or collate function, which basically specifies how individual data samples should be merged in a batch. So there are various things you can do with that. In here we are just using it to use a batch size of 32, and we want to shuffle it. So let's run this, and if you want to have a look at the type, Now this is a data loader type of the torch geometric which we would train our model on. And length of this is 105. So basically 105 batches are there, because here the batch size is 32. So basically in one batch there are 32 samples, and we had 3 samples in our training data, so around 105 batches. So that's what it's showing here, 105 batches. So it will basically train the model in batches. So our training and test sets are ready now. What we are gonna do is we are gonna be defining our model. So first we need to define a device. So it would be CUDA. If CUDA is available, else CPU. So basically we will push the model and data to the device, and if you have a GPU available, it would utilize that facility to load and train the model. Otherwise it would just use CPU. And the model that I'm using here in this graph neural network project is Attentive FP. So I'll take you to the Pytorch geometric documentation, and in here in the torch geometric.nn section, if you go to models, down here you will see information regarding Attentive FP, and this is actually a graph convolution neural network model designed for molecular property prediction. It is one of the most advanced graph neural network model. As you can see here in the description, the Attentive FP model for molecular representation learning, this is the reference paper based on graph attention mechanism. So this uses the attention mechanism for training. So you can see here in the index here we have input layer, attentive layers for atom embedding, attentive layers for molecular embedding, and then we have the task layer. So this is mainly designed for solving chemistry based problems like solubility, affinity, toxicity, side effect, or for property predictions. So that's what we are going to be using today. In here, so basically what I have done here is I have imported Attentive FP from Torch geometric models, and it takes in various parameters. In channels here is equal to the number of input sample or number of node properties. So if you go here, if you just print out one of the data point, so this is the graph structure of one of our compound. As we already discussed before, the first number here represents the number of nodes, and this here represents the number of node attributes. So this goes in here in channels. Hidden channels are basically the number of hidden features per node in the hidden layer of the network. This is a hyperparameter. You can use 32, 64, 128, and in the next lecture, when we will talk about hyperparameter tuning, we will change this variable. Output channel is 1 because we are dealing with regression task here, and we just want one numeric output. So the output channel is 1. Edge dimensions or edge feature is this one over here. So we have used just 3 edge attributes, so this goes in here. So in channels and edge dimensions are fixed throughout the data set. Number of layers basically represents the number of graph convolution layers in the model. You can use 4, 3, 2, 1. Again, this is a hyperparameter, and each layer learns progressively more abstract representation of the graph. Number of time steps here represents the number of time steps or iterations for the attentive readout mechanism. Here we have a value of 2, and in the attentive readout phase, the model will perform 2 iterations of the attention to aggregate node features into a graph level representation. Dropout is 0.2. It's basically the dropout probability for the dropout layer, and it is a kind of regularization technique which is used to prevent overfitting. And then we are pushing this to device. Again, if you have a GPU support available, we will push our data to and the model to the device so that your training is faster. Optimizer, here is Adam optimizer, which takes in parameters as model parameters, learning rate and weight decay. They are again the hyper parameters which can be changed. Learning rate controls how much you want to change the model parameters in response to the estimated error each time the model weights are updated. And weight decay is a regularization technique that adds a small penalty to the loss function based on the size of model parameters. This helps to prevent overfitting by discouraging the model from having large weights. So we can run this and we can print out the model as well, model parameters. So this is the model that we are using with all these parameters here shown here. And okay, so now we have defined our model and optimizer. We can just go ahead and define our train and test functions. So what is train function is basically, so def train basically means once we run this train function, it should start training. So that's what we want to achieve here. And for data in data loader, so basically it will iterate through each batch. So in the first iteration, first batch containing 32 data points will come into picture. So this line of code here, like here we have pushed the model to the device. Here also, if you have a GPU support, it will just move the data to the specified device. It could be CPU or your GPU. Or optimizer.zeroGrad, basically this clears all gradients from the previous step. And in the next line of code here, this is basically a forward pass. It passes the input data through the model to get predictions. So data X, data agenda X, data dot attributes, all these are the components of a graph dataset that we have discussed in the previous videos. And this is our loss function, and it will calculate the loss by subtracting the predicted values with the actual values. And loss dot backward would compute the gradient of the loss with respect to the model parameters. Optimizer dot step updates the model parameter using the computed gradients. And then over here what we are doing is we are adding the current batch loss to the total loss and adding the number of graphs in the current batch to the total samples here. So finally we just we will calculate the root mean square error, because this is the mean squared error, and when we do a square root, that would be root mean square error. So this training function would return us the root mean square error. So this is the training function, and then this is the test function. Again, you can kind of use the same thing over here, but I've just made it a little different here. This would take in argument as your loader. So it could be test loader, it could be any other external data that you have. And then you need to put in model.eval while you are evaluating your test data. Again, it will iterate through the data in the loader, push your data to the device, CPU or GPU. Then it will here pass the input through the model that we have trained to get predictions. We'll calculate the loss function here, and we will append this to this list here, and in the end we will just calculate the mean and square root, so mean squared error. So this is root mean squared error, and that's what we will return. So yeah, that was all about training and test function. So I think we are all set for training our model. And what we are doing here is that I'm storing these train and test scores, which are root mean square error loss. And why I'm doing that, I'll just talk about that in a minute. I want to train for 50 epochs. You can do more, 100, 150, but since I am just using Google Colab here on CPU, it takes a long time. So I'm just sticking with 50 epochs. This is a highly important parameter, especially when you're using Google Colab. You do want to reset your parameters every time you run it. Otherwise, it will just start from where you have left. Again, for loop for epochs, this is the train root mean square error this is the train function that we have defined, which would return the root mean square error. So this would be train root mean square error. Of course, the test function here would also return us the root mean square error of the test data set. We will append these scores in here to the score underscore train and test lists, and then I want to print out the train loss and test loss, as well as in the end I want to plot a line plot of epochs versus our training and test loss. So that's what I'm doing in here. I'm using matplotlib to plot the these things, epoch versus the loss, and these are just the labels and these are just the legends. So let's run this. And so as you can see, for epoch 0 we have training loss of this and test loss of this, and in the next epoch it's coming down here as well, it's coming down a bit. So let's wait for it to finish and then we will evaluate our results. So the model has finished training, and as you can see, with increase in the number of epochs, the training and test losses have come down. And if you look at the numbers here, we started with 1.35 and it has come down to 0.587 for train, and for test it's around 0.713. And yeah, now let's so these are just losses, right? I want to see the R-square values, and I also want to see the predicted values, and I also want to know the smile strings for my predictions. And just I have written here another function called eval, and it's pretty much similar, except that I want to return a data set which has the predicted values, actual values, and smile strings here, and it would also print out the R2 scores here. So let's run this and evaluate our test set. Now the R-square for the test set is 0.63, and if you want to see the data set itself, this would be our data set with predicted values, actual values, and smile strings, so that we can further analyze it. And for the final test set, if you want to see the root mean square error, I am just using the mean squared error function, and I am just doing a square root of it, and it is 0.713, which is the same in here. Now for the train set, if you want to do evaluation, the R-square is 0.767, and this would be the data set itself. And if you can also just copy paste this in order to calculate the root mean squared error, except that we need to change it to train. So this is 0.582, and just I want to take you to the reference here for the lipophilicity, and this is the kind of reference, MolecularNet, a benchmark for molecular machine learning. And if you go to the PDF, down here, so these are the benchmarks. Now we are dealing with lipophilicity here. So lipophilicity root mean square error for XGBoost, the root mean square error is 0.799. For graph convolutions we have 0.655. so this is the best one in here. And just one point here, we just ran for 50 epochs, right? So I think if you run for more epochs, we could be pretty close to 0.65, and this is right now 0.713. so I highly suggest you, if you have a workstation, just run for more epochs, maybe 100, 150 or 200, and see how low you can go. You can just consult this reference over here. I will provide the link in the description. This is the benchmark here, and I think we are kind of in between the XGBoost and these graph convolution, just because we have ran it for few epochs here. So yeah, that's kind of an assignment for you. Just take it as an assignment and run on your own. Yeah, just one last thing I wanna tell you is how can you save this model. All you have to do is torch.save, and then the model, we have the model here, and just the path with the name with which you wanna save this model with .pth extension. So just run this, the model will be saved in here. So this is the saved model, and you can load this model via this command torch.load and the same path. And if you run this evaluation again, the R square is pretty similar, 0.61631. Here also 0.631. So this is how you can save your model and load your model. So in the next video we will talk about hyperparameter tuning using Optuna, and stay tuned. Thank you for watching.